Hello, everybody, and welcome to the third Thursday Science webinar of the European Marine Board. Thank you very much for being here. It's really nice to have this first Science webinar of the year. My name is Sheila Heymans. I'm the Executive Director of the Marine Board, and I will be your host today. So today, if I can move my slides, just some quick housekeeping rules. Please make sure that your name is clearly entered when you speak so that you can ask questions, so that I know who you are when you're asking questions. Please put your questions into the Q&A. And when you do so, it would be nice to know where you're from. And I will pick the questions after the webinar, after the talk, and speak them to Christophe. If you have any technical issues, please please use the chat and we will see if we can help you. Be aware that this webinar is being recorded and it will be made available on our website and on our YouTube channel. So without further ado, just to say that the webinar today is about data science for offshore renewable energies. So what are the data availabilities and the requirements that we need for metocean analysis? This is obviously linked to our future science brief on European offshore renewable energy towards a sustainable future, our future science brief number 9. Then, next, just to say that the talk will be given by Christophe Maisondieu. He is a senior researcher at IFREMER, the head of IFREMER's Marine Hydrodynamics Laboratory, and he was the chapter lead for the review of European offshore renewable energy status. So I will stop there and thank you very much. If you can stop sharing slides. And Christophe, very nice to have you here. Please go ahead and share your slides, and you have half an hour or so for your talk. Thank you.
Okay. Thank you. Thank you, Sheila, for this introduction. You should be able to see my slides full screen now.
I don't think it's in full screen.
Isn't it?
Yeah, now it is. Now it is. Sorry, maybe my computer is a bit slow. There we go.
No problem. Thank you. Yeah, so as Sheila said, in the future science brief produced by the European Marine Board, we provided a set of recommendations, and one of them was to support measures to increase the availability of open and high-resolution data to understand offshore renewable energy resource availability, environmental impact, and the impact of climate change. So in this presentation, I will try to provide more information, basically through 2 angles: the use of ocean data in site assessments, resource characterization, and device design. And also I will address the gaps and needs in data availability and measurement capability. To do so, I will share this presentation into 4, I would say, sections: offshore renewable energy resource mapping, requirements for design and operations, data availability and measurement capacity, and finally, data access and databases. So offshore renewable energy resource and mapping. So you recognize here the Earth with a thin atmospheric layer. The Earth is rotating around its axis and submitted to gravitational forces, and it also receives solar radiation. So the gravitational forces will generate sea level variations and currents, which are the tidal currents. And so from these sources, we can extract potential energy through the development of tidal barrage or tidal lagoons. And we also can extract the hydrokinetic energy using, for instance, tidal turbines. The solar radiation is a driver of the main ocean atmosphere exchanges, and it provides heat at the surface of the planet. But this energy is not evenly distributed, hence we have variations in temperatures and pressure, and this imbalance in pressure will be compensated through the generation of flows of the wind. And one interesting feature of this wind is that when considering offshore wind, compared to onshore wind. Sorry, offshore wind is usually stronger and less turbulent, and thus is more energetic and stable. So, of real interest for extraction and for renewable energy. Waves. So waves are derived from the transfer of wind energy to the ocean surface. So the waves are considered as a random process. It's a combination of different waves having different frequencies and direction, and so they are randomly distributed. And the wave energy is what is important here, is that wave energy is distributed in both frequency and direction. We can have, of course, waves where the wind travels, but where the wind blows, sorry, but they can travel also outside the areas where the wind is blowing, and this is swell. So we have in many areas really complex situations and sea states with different wave systems. There is another result of the solar radiation. It's the ocean circulation, combining wind-driven inertial currents and thermohaline circulation. Examples of these are the Gulf Stream and Kuroshio, relatively strong currents, but we'll probably not get into this today. So about resource assessment. So the main objective of resource assessment is to characterize the availability or the available power and the way it's distributed at the surface of the oceans. And so this resource mapping is usually built combining different sources of data, and the main three sources of data are numerical modeling. We will rely on hindcast data sets, in situ measurement, and also remote sensing. So from these different sets of data, we are able to provide a mapping of the energy associated with these three sources: wind, waves, and tidal currents. This mapping has been connected for decades already. It's an information that has been available. It's regularly updated when the data sets are improved or updated. So these studies on resource assessment clearly show that whether it is for wind or waves, we have an interesting resource here that can be used to respond to the demand of energy and mainly of electricity at the global level, also at the European level, of course. Tides and tidal currents are also available, but in I would say in more restricted areas, because it's important for proper extraction that we can have strong enough currents with high velocities above 2 meters per second. And so only a few locations are available that provide this kind of these high velocities. When we study the evolution of the distribution of these resources, what we can see is that there is a clear regional distribution. The energy is not distributed regularly everywhere. And there is also a seasonal time variability, a seasonal and inter-annual variability. We should also not forget that these processes we are studying are random processes, wind and waves, and pseudo-periodic or sometimes random processes for currents, and pseudo-periodic for tidal currents. So in order to really build relevant resource characterization, we will require long time series of relevant parameters, such as wave height or wind speeds, for example, to build the statistical assessment that will provide all the necessary information, and to build the climatologies that are necessary for the engineers. We also have to consider that there is a requirement for a sufficiently refined spatial discretization, so that we make sure that we can catch all the physics of the phenomena that we are studying and that we are modeling or measuring. So this is for resource assessment, and if we what we are interested in is the exploitation of this resource. And so we need to design structures and deploy them. These structures are meant to extract the energy of the wind, waves, and current, and to convert it mainly into electricity. There are other forms of conversion, what's called the power to X, but we mainly focus on electricity production. So we have offshore wind turbines for the wind tidal turbines and wave energy converters. So for the design of these structures, and also considering the marine operations, we have to keep in mind that these structures will be deployed for a very, very long time, a couple of decades at the minimum. So they will face a really complex marine environment, combining everywhere wind, waves, and current. So the objective of the design is to make sure that these structures are efficient. That is, that they will produce, that they will convert the energy from the waves or the wind efficiently into electricity. This is really important because with the objective of the Green Deal to really use offshore renewable energy as a good support for the development of the objective of the Green Deal, it will require development of a large number of structures. And so there are some industrial issues here, and by optimizing the efficiency of the machines, we can address this problem of industrial production. The reliability also is really an issue. This is related to the aging of the structure, to the cyclic loading, and also the response to extreme events and the loading associated with the extreme events. Of course, we have to operate these machines, so they are to be deployed and regularly maintained. So this involves a large number of marine operations. All these actions also have one clear objective. It's also to lead to the reduction of the levelized costs of the electricity. So it's a major issue for the engineering. Yeah. And we also have another aspect that we shall not forget. It's the environmental impact. As when we deploy these structures at sea, we know that they will have some impact on the environment, whether it is negative or positive, and we have to find a way to assess this properly. Sorry. So regarding the offshore wind turbines, if we look at the wind information, so we have power spectral density that gives us information on the long-term viability of the wind. So this is what provides information on the interannual and seasonal viability, but it also goes all the way down to periods of 24 hours to 10 hours, so diurnal or semi-diurnal. We are mostly for design, we are mostly interested in wind speed short-term viability, the variations within a minute, which are associated with turbulence or some transient events. These will have an impact on turbine efficiency, but also on turbine fatigue and also extreme events. So really important for the designs. The variation at the scale of the hour or a few hours are of less relevance for the design itself, but more for the operation and the production problems. We also have to take into account the fact that the wind speed is not evenly distributed, or is not evenly distributed in the boundary layer for these wind turbines, which are really high, up to about 200 meters above the sea level. We will have to assess also the evolution of the wind profiles in the boundary layer. So if we take all this into account, we see that the requirements for wind data are long duration time series of wind velocity, intensity and direction. This to assess all the variation within minutes, but also long-term to build long-term statistics. This requires high frequency sampling, and also we have to be able to measure or to model in the lower layer above the ocean, but still to relatively high levels. We also have to consider that these wind turbines will be deployed in farms, so that the turbines' efficiency might be affected by the upstream turbines. We also have to optimize the layout of all these turbines. We are talking about 100 of turbines per farm sometimes. This also will have an impact on aging, and as we can clearly see on the picture, we cannot neglect the environmental impact these large farms may have. There are other issues also, mainly related to the case of floating offshore wind turbines or planted or offshore wind turbines. It's the impact that the waves and the current on top of the wind will have on the design of the structures. So we'll have floating structure dynamics will have to be assessed, but also the extreme loading induced by the waves. Same for the moorings and the export dynamic cables. The loading will be induced mainly by the waves and the currents. So it's really important that we assess this as well. So for all this at the farm level as well, we need refined special grids all for the modeling or for the information that we get at the regional or at the site scale. We need also to have access to joint parameter databases, joining wind, waves, and current parameters. And since we are building statistics to assess the extremes as well, we will also need long duration time series. When we look at wave energy converters, the main information we require is information on sea states. So this is for to assess the dynamics of the structure and the response of the structure. It's also for the optimization of the power takeoff. This also sometimes requires the development of control methods, which are really which require information, I would say almost wave by wave. These structures will be moored, and we also will have export cables. So we will have to study the influence of waves on these. Of course, once again, a major issue is the assessment of the extreme loading. These are values, return values considered here are 50 years return values, or even 150 years values. 100 year, sorry, return values. In the case of these wave energy converters, we also have to assess the survivability, which is actually the level of energy in the sea state above which the converters cannot work anymore for safety reasons. And so this is an important parameter in the design and the operation of these wave energy converters. So to answer all these questions and provide all the relevant information to the engineers, what we need are long time series of both spectral directional spectra, long time series of the integral parameters, namely significant wave age, periods, and directions, for instance. This information should be available on refined spatial grids, certainly at the site scale, but also at the regional scale when we consider wave energy production and also environmental impact. And as I said, we also need wave by wave information for control, but also for the risk associated with wave breaking and impact. When we look at tidal turbines, the objectives are relatively similar. We seek to optimizing the turbines. We also have to adapt the control methods. The turbines and the blades are to withstand extreme loading as well, and fatigue aging. And when we consider farms of these tidal turbines, we are to also characterize the wake of the turbines. This is to optimize the layout, because downstream turbines might be impacted by the wake of the upstream turbines. and this also, of course, may have an impact on the environment. In the case of really energetic flows that we have at the tidal energy production sites, what is really important is to characterize the flow variability and also the turbulence. It's relatively straightforward to get the mean velocity, but but there is a strong variability and also turbulence structures in these flows. And these are really important for the design of the structure, because they really will affect both the efficiency of the machine and also their aging. And we shouldn't forget about the waves, because waves, these tidal turbines usually are deployed in relatively, I would say, in intermediate waters, where the impact of waves and the wave kinematics can be measured very low in the water column. So it might impact, and it will impact the turbines themselves. And this really has a clear impact that was identified on the aging and the efficiency of the machines. So again, for tidal turbines, we need high frequency current velocity time series, that is high frequency sampling, water levels time series, maybe not with the same sampling frequency. We also need refined bathymetry, and we also need information on the sea states, both parameters and spectra. If we look at the marine operations, in order to deploy and to maintain these structures, we have to assess weather windows. That is a period of times during which the weather, or I would say mainly the wave height and wind velocity and current velocity will stay below a given threshold. So in order to do that properly and to establish these weather window, we need to build joint statistics combining information on wave, wind, and current. And we also have to address this at the regional scale. When I talk about regional scale, I mean in the area between the harbor where the supply or operation vessels are located down to the production site where the structures are deployed or to be deployed. We also require short-term forecasts for operation planning. This is really the last moment, go or no go, and also for safety reasons as well. And we will need on-site real-time information for conducting the operation in safe conditions. So this means wave detection, current velocity measurement, and wind velocity measurement. So for all this, we once again will need a long time series of the joint parameters for wind waves and current forecast data and in situ measurement. When we look at the aspect of the environmental impact, so here I'm not talking about the impact on the on fish, on the halieutic and benthic life. I'm mostly addressing the physical parameters, that is wind speed, wave height, current velocity, but also temperature, salinity, or sediment transport. Because any variation, anyway, of this parameter may affect afterwards the fish and different species in the water. So the main elements we have to address here is the characterization of the influence of the machines and moorings on the flows, on the currents, and also on the water elevation in the area of the site production, but also in the wake downstream. So that is really important because the farms will be of large dimensions, and so the wake will be really large as well. So to get this information, once again, we need most probably model data at regional scale and using refined grid. We will also need in situ monitoring for measurement and validation of the wind, wave, and current parameters. We also need, we could take advantage of remote sensing for both local and regional assessment, and mainly the effects associated with a wake downstream in the farm. So if we now talk about the availability of data, so if we consider in situ measurement, and first the first is for wind. So usually, I mean, so far information, local information was obtained from met masts. These masts were equipped with a large number of sensors, mainly anemometers, but different kinds, also different kind of radars or other sensors. They are considered as the reference still at the moment. There are a couple of drawbacks. They are very expensive, and their use is restricted to, I would say, shallow to intermediate waters, water depth areas. So more and more they will be, or they are replaced by LIDAR, these laser imaging detection and ranging systems. These systems are able to provide some information on the wind profiles up to the requested 200 meters height. This is really interesting measurement systems. However, they still have a few drawbacks. They produce a large amount of data, and the processing is not always straightforward. The processing is based on theoretical assumption for wind profile recomposition that must be validated everywhere. And also in the case these LIDARs are placed on a floating structure to get closer to the production structures that are deployed, then we will have to compensate or to correct the influence of the platform motion on the wind measurement, and this is still relatively tricky. For the waves, the major in situ measurement system will be wave buoys. They are still considered as a reference. So we have a float which is equipped with an accelerometer or GPS, and it provides wave by wave information on the waves, wave height and period, and as well as direction. So it also brings information on frequency and direction distribution. So the 2D spectra. There could be some improvement there as well. The methods for identification of the direction and directional spreading could be improved. And yeah, there is also not really an issue, but improvement to be conducted on the characterization of the multimodal sea state composed of the superimposition of different wave systems, wind, sea, and swells. Another tool that we can use is the acoustic Doppler current profiler. This initially was designed for current measurement, but it's also suitable for wave measurement. Usually it's best to combine it with current measurement as well. And it's really reliable in intermediate waters, but when we have to go into a deeper water and fix the ADCP on the mooring, then we have some motion compensation measurement to take into account as well, which also makes it a bit tricky. We can also use pressure sensors, but these are really limited to shallow water areas and a circle. So, well, these elements are just a limited list of what is really available, but these are the most widely used systems. For the current, as I said, we can use acoustic Doppler current profilers, which will provide information on the current velocity all along the water column. So it's well adapted to the mean velocity profile measurements, but when we look at high resolution and high frequency turbulence and variability assessment, there is still some improvement requested, both at the technical level, but also on the methodology and the validation on the assumptions that are used for the processing of the information. Once again, this provides large amounts of data. We can also use acoustic Doppler velocimeter. So these are based on the same principles as ADCP, but they have converging beams so that we can have a local measurement, which can be of really higher precision. But it's sometimes really difficult to compare measurement connected with ADCPs and measurement connected with ADVs. And the third system we can use is HF radar, which offers a relatively wide spatial coverage. We're talking about a few tens of kilometers, up to 100 kilometers. It provides near real-time information, but well, the grid is probably not always refined between 1 and 2 kilometers, but it's relevant information for surface current. So this was for in-situ measurement, just a brief insight. And regarding remote sensing, so since the, I would say, mid-70s, a large number of missions have been launched with satellites equipped with different measurement systems like altimeters, scatterometers, or synthetic aperture radars, having the capacity to provide information on wind, wave, and currents. So the main advantages of the remote sensing is the global coverage. We have relatively widespread measurement zones. I would say the footprint of the altimeters is of about 6 to 7 kilometers in diameter. And nowadays we have a long duration time series of continuous data, between 30 and 40 years of data. So it starts to be really interesting to help building statistics. However, we have some limitations. The time and space discretization, the return period of the satellites is relatively long, a few days, usually between 10 days and 30 days, but we can combining different satellites, this can be reduced, but still there is some time discretization. And also there is a space discretization with the intertrace, which can reach about 100 to 300 kilometers. The method to get access to the information that is relevant for the engineer, these processing methods are relatively complex. The satellite information is to be calibrated and validated, and this is done against this in-situ measurement or other sensors, but not against a numerical model, of course. And also the quality of the measurements will be affected by harsh conditions, strong winds and high waves. However, remote sensing is really valuable for enhancing knowledge, the calibration and validation of the numerical models, and also for the characterization of the sites of the production site with the kind of information at the side of a wind farm, for instance. And this is interesting for environmental assessment, for instance. So the third source of information is numerical modeling. So these numerical models will be developed for atmospheric information, but that is wind, but also for wave propagation and current propagation. So the principle is basically the same. We have an equation which describes the physics of the exchange between forcing fields and the output, which is, for instance, wave energy density for the wave models. So these models, they will require information as input, like the bathymetry, seabed roughness, or coastline contours. For the wave models, the inputs will be also the wind fields and the current fields and water levels, and so on. The physics in the model is described by parametric models, just characterizing, for instance, the energy transfer between wind and waves, or the wave-wave interactions, for instance, but also all the energy dissipation. So one issue here is that these models are parametric, so we have to adjust these or to tune these parameters depending on the input data we provide. So there are many advantages in using numerical modeling. So it provides global to local coverage. That means that we can start from global, but we can go we can downscale to reduced areas, like the size of a farm, for instance. So we can refine the grids almost as we want. We can produce long time series of data, and that is really important for building climatologies and building statistics. There are some limitations, the main one being probably really, as I said, related to the fact that we have parametric models, so that we have to calibrate and validate them, and this is a relatively complex process. There is also a problem of data storage and handling, but it's really valuable for, as I said, building climatologies and also for knowledge enhancement. Yeah, as I said, calibration and validation of the numerical models is really crucial, and this is made against in situ data and remote sensing data. One issue here is the fact that we don't have many databases in coastal areas, in intermediate waters, I would say that, or close to the shore. I would say that the number of wave buoys, for instance, in water depth lower than 20 meters is really limited, so that we don't have real information on the quality of the numerical models in these intermediate waters. And same for remote sensing in close to coastal areas. The information is not as reliable. But it's combining these two sources of information is really relevant for calibration and validation of the models. Yeah, once the production structures are deployed at sea, they are to be monitored during their whole life. So the production at site is, or the production sites are monitored for different with different objectives: production management and optimization, management of the operation, monitoring of the aging of the structures, and also for the purpose of environmental impact assessment. So the requirements here are the local in situ measurement with a in that case, we don't really need as high sampling frequency as for the other activities, but we will need information on the joint parameters, wind, waves, and current, and we can make use of remote sensing here again for the study of specific events, and also for environmental impact assessment. Yeah, I would like to just add one thing, one point about laboratory measurement. I would say that it's a really interesting complementary data that we can get through laboratory measurement. It will contribute to knowledge enhancement of the physical phenomena that are at stake here. And it also provides information for the validation of the models, whether they are just theoretical or parametric, that will be implemented in numerical models. Well, there is, the difficulty here is that it requires adapted similitude laws to properly take into account the scaling effects. But it's interesting complementary data, I would say. So this is it for this overview of the different data sources. Now we can talk a bit about data access and available databases. So the requirement for ocean data we've seen is that we need to combine the use of the three available sources of information: numerical model, in situ measurement, and remote sensing. So in order to do that properly, we have to make sure that we have the capacity to cross-validate the information that we receive from these different sources. It's the best way to make sure that we use the most relevant data and that we have proper information, and that is critical. Yeah, I will rapidly go through this. It's requirements for ocean data. So in dark blue, you have what is required, but that is already available. but could be improved. And in light blue, we have probably points on which we should work a little bit. So for ANCAS databases, numerical models, we need a long duration time series to build statistics and assess the extremes. Refined grids at the regional and site scale, co-localization of the information, and also spectral directional information for structural design. We could improve parametric models, consolidate the quality or the validation of the forcing fields, and also take advantage of the development of informatics to improve or increase the resolution. Regarding in situ measurement, what we need are at least a pluriannual time series for site characterization and also for models validation. This information should be co-localized and also provide wind, waves, and currents together, and also high sampling frequency for spectral information. For in-situ measurement for both wind, waves, and currents, we could improve sensors and measurement capacity, also processing methods for these sensors. Regarding remote sensing, so the benefits and what we can use are the long duration time series again, the fact that we can have access to co-localized information for wind, waves, and currents, and it's a good support for enhancing knowledge. Yeah, something, I don't know how this could be done, but if we could improve time and space discretization and measurement capacity in harsh weather, that would be really interesting. Regarding data access, again, I would like to insist on the fact that information should combine with wind, wave, and current and be co-localized on the same location. We need to make sure that we have a common nomenclature for all the parameters that we use, that these parameters are also adapted to the needs of the engineers, that they can be really used. The metadata associated with the databases should be really properly informed, and we should use standard data format to facilitate extraction. Just a few words about these extraction tools. We need to use some advanced tools that allow for quick and easy extraction of data, whether it is maps or time series. Data should be, of course, as much as possible offered in open access through referenced repositories and be referenced using, for instance, digital object identifiers. Yeah, I have provided a list of usual reference data sets, but maybe we don't have time to go all through this. So I will just list them here. And just to conclude, I just would like to give a quick comment on climate change. So it's clear that climate change will have effects on the offshore renewable energy sector and the production of offshore renewable energy. Probably the only way to assess this impact is through, of course, through numerical modeling. But there are still some requirements. So we have to base this assessment on commonly defined scenarios and data sets. We have to develop tools for downscaling at the regional and site scale, which is really important. And we have to work on the reduction of the uncertainties. So basically through defining common statistical models and metrics, and to find agreements on the physics implemented in the models and the assumptions that are made in these models. So this was just a brief comment on the assessment of climate change, but surely it will have an impact on offshore renewable energy. Well, thank you. I think we will have questions now.
Yeah, thank you. Thank you very much, Christophe. That was great. I don't know if you want to just stop sharing it. There we go. Perfect. So people can see you well. Thank you. That was a very comprehensive overview. And I see we have at least one question in the Q&A from Cecilia Bertozio from EDF Renewables. She asks, What is your opinion regarding the relevancy of the wave data measured by sensors deployed on floating LiDARs? What would you say? Would you say that they are accurate as data measured that they are as accurate as data measured by metocean buoys?
I'm sorry, I'm not sure I understood. Is it measurement of?
Yeah, so she's saying data measured by sensors deployed on floating LiDAR.
Okay, but it's
LiDAR,
wind.
sorry.
Yeah, it's wind information.
Yeah, maybe she means other data. You know, if you have sensors on these floating LiDARs, if they have other sensors that measure other things, I don't really know. Maybe Cecilia, you can elucidate more. But yeah, I don't know if you have any questions. While if we get a better question from her, I will go into some of the questions that we've got at the from the Marine Board side. The first one, I guess, is how successful do you think that the current hindcasting and numerical models are in predicting climate and weather conditions, which obviously is getting more extreme? And is there a risk that we are under predicting conditions that we are actually experiencing? So maybe I'll leave with that.
That's a tricky question. I'm not sure I have the answer to. It's really difficult to assess. I mean, if we look at the models at the moment, yeah, I would probably mainly focus on waves. The information we have is quite, I would say, is quite good. It can be improved, but it's quite good at the scale of a wave energy converters farm, but also at the scale of a wind farm, for instance. It would be probably not as good in shallower areas. As I said, below 20 meters, we really have to verify this. But for the time being, we can be confident on the quality of the data we have for waves, and for currents. It's probably not as reliable, in the sense that the models don't provide all the necessary information on the variability, and also what's associated with turbulence at the scale of the structures. So there is more to do there, but still we have relevant information. And regarding the evolution associated with climate change, the problem is that there are the level of uncertainty we have between the different databases is still quite high, and it's between the models that are used. There are differences that makes them really difficult to compare. So it's really difficult to assess this, and the actual efficiency, even with the ensemble methods, it's really difficult to assess the quality of this assessment.
Yeah. And just a follow-on question that comes from the Q&A, Ines Mercado asks, what's your opinion on the main effects of climate change on offshore renewables, so wind and waves? And do you think there's a pattern, or will this be more locally specific?
Really, that's regarding climate change. At the moment, I really wouldn't take the risk on having a definite opinion on what's going to happen. It's clear that there will be, I mean, yeah, there will be local changes. There will be probably stronger storms and stronger events, but where they will be located and with which return values,
it's hard to know.
It's really hard to know. Yeah.
Okay, and then Cecilia also came back to say, yes, she's indeed talking about wave measurements by sensors located on floating LiDARs, which are large structures and larger than metocean buoys.
Which are larger than metocean buoys.
Yeah. So I guess the point she's making is that how accurate is it compared to meta-ocean buoys if they are bigger structures? How accurate is the data that they would measure for waves? I guess that makes kind of sense to me now that I know.
I don't know which kind of sensors she's referring to. I would say if the structure is big enough so that it's a fixed structure, then it's probably interesting. But if it's based on laser measurements, for instance, it will not necessarily provide all the information regarding directional distribution, for instance. So it's
maybe it's a conversation you guys should have sometime. She's saying the floating lidars are more stable than the metocean buoys. So, do you think they would be more accurate to measure?
Yeah, but that would be using.
Because I'm assuming the buoys would.
Yeah, the float itself will probably not be as good as a wave afloat, as a wave buoy, because the wave buoys are designed for that. And, if the float itself moves less, then it will filter out part of the wave information. But if it's other sensors placed on the float itself, well, probably it depends on the kind of sensor you're using.
Yeah. And then maybe I can carry on with that, because we were talking about sensors and buoys. Another question that came from Paula, who you will remember from the working group. She can unfortunately not be here today, but she asked me to ask you. She said there's a lot of structures already in the water, oil and gas platforms and so forth. And there's obviously more and more being installed as all the time. So would it be feasible and useful to put sensors and measurement instruments on all of these to help gather some of the data that we need? Or do you think there's still not enough spatial resolution? Is that still inefficient?
No, it will be interesting.
Insufficient.
No, it certainly will be interesting to place sensors on the structure that will be deployed. Maybe not all, but on a sufficient large number of platforms. It will complementing the information, not just for the operations, but also to gain on the knowledge, and that will be more. I guess that will be also more and more requested for environmental impact assessment. We need information on wave, current, and wind to also validate the other information or to assess the other information.
And then Paul also had a question about who do you think should be responsible for making sure that the data that's needed is gathered and made available. You talked a little bit about open science or open data. Do you think it should be the industry? Do you think the regulator should make that compulsory? Or should there be somebody else?
I don't know. I don't think. I mean, the developers, the industry. I mean, they could at least provide the support, provide the access to the structures, for instance, so that the information be deployed. But probably all the programs that are necessary, whether it is for in situ modeling or remote sensing, they probably should be monitored at a higher level to make sure that this environmental data is available for everyone. There's been already a relatively important evolution over the last decade. We have more and more openly access to environmental data, and this is through the development of the regulation, but also the development of programs, research programs aiming at developing new databases and new models, for instance. So it's I would say it's important that this access to the data be not limited by what is provided by the industry, and we shouldn't probably force them to share all the information. I'm not sure they would be happy with that, even though environmental information is is not really a secret.
Yeah. Then there was one other question, which I think is quite a valid one, that, you know, with the Green Deal, there is a requirement that we put quite a lot of renewable energy in the water. And I guess we have relatively good data in the North Sea, but what about the rest of the European seas? Do you think that we will have the data and knowledge necessary in the other seas to be able to do this well?
Yeah, I think it's the case in the Channel and on the Atlantic coast. We have quite relevant, quite accurate data sets. It's probably more difficult in the Mediterranean and in other semi-closed areas, for instance, with shallower waters. So yeah, there is probably an imbalance also in the quality and availability of data, depending on the areas. So this is probably something we should work on.
Yeah.
I haven't really assessed that, but it's a good point. Yeah.
Yeah, it's definitely something I think that needs to be looked at, given the requirements that the Green Deal has. Okay, I don't see any other questions. Maybe, Jana, if you can put the last slide on, then while you do that, I will just say thank you very much to Christophe. That was a great conversation. It was really interesting to see what's being done so far and what's still needed in order to make this renewable energy happen, and certainly to understand more the kinds of information and data that's needed. So thank you very much again, Christophe. And thank you very much for your hard work on the document. So then it's just for me to say that our next webinar will be on Thursday, the 15th of February, and it will be on blue carbon and nationally determined contributions, specifically on financing blue natural capital as a nature-based solution. And it will be by Torsten Thiele, the founder of the Global Ocean Trust. So if you're interested in that, please register online. And thank you again very much, Christophe, for giving us a great webinar, and for working so hard on the Future Science Brief. And with that, I want to thank everybody for their time, and hope to see you again next month. Thank you.